Thank everybody for coming out here, and thanks for hosting us today. Who we are is a small team associated with the Strategic Studies Institute and the U.S. Army War College, where we've been looking at how the Army integrates artificial intelligence. And the lens through which we look at it is through its impact to the profession. And I'll talk a little bit more about what that means here in a second. But we're going to talk about the kinds of challenges that we're experiencing and offer some recommendations on what to do about it. But I love to start with this quote from Boris Johnson, where he, in a 2019 speech to the UN General Assembly, he warned of the effects of all sorts of disruptive technologies. And while he covered a wide range, he included artificial intelligence. And his quote kind of makes a point. Often with these kinds of technologies, they raise as many problems as they solve. So to respond to that challenge and deal with the problems that get raised, and in the spirit of great decisions, the integration of artificial intelligence is going to force the following decisions. To optimize the technology, it generally means greater dependence on the machine itself. And that greater dependence cedes at least a little or some, perhaps a lot, of human control, which comes with certain risks. So to decide how much control we want to cede to the machine, we have to figure out what our tolerance of risk is. So we'll be talking about risk a lot today. Now those decisions will inform the kinds of technology we invest in and employ, and how we employ them. With that in mind, we then have to decide what kind of people do we need to develop and maintain such systems, as well as what roles they'll play. And to get there, we have to decide who is going to be responsible for developing and implementing this technology within DoD, and where our focus is particularly on the Army. But in both, there are a lot of top-down as well as bottom-up processes, and finding the right balance can be something of a challenge. Now, AI technologies pose a particular kind of challenge that lots of other technologies, don't. So, for example, unlike previous arms races, like the race to the atomic bomb in World War II, expertise for artificial intelligence lies largely with industry and academia, not the Department of Defense. Moreover, effective employment of the technology can't be relegated to just a few specialists. Not everybody needs to be a pilot to have an effective Air Force. However, what we're finding is almost everyone will have to develop some level of AI and data literacy if the US military is to realize the full potential of these technologies. So given these conditions and the way they're going to have to be employed, we're thinking about how it's going to impact the profession. So to do that, as I've noted, we're drawing at least some of our lessons. We have a wide scope, but we're drawing some of our lessons from Project Ridgeway, which is an effort by the 18th Airborne Corps, a very ground-up effort to become AI ready at the operational level. You see behind me our agenda, and basically, to rise to the challenge, the Army first must understand how the use of AI impacts its expert knowledge and the subsequent barriers to trust that impact generates. And so we're going to cover that first. I'll first talk a little about the relationship between expert knowledge and professional status, the impact of AI on that expert knowledge, and then the rest of the presentation we'll then look at how to overcome those barriers at the operational level, as well as suggest institutional and strategic changes that may facilitate AI integration. As we go along, a couple things to pay attention to. One is that there are two levels to this discussion. First is what it takes to employ the technology effectively, as well as what it takes to manage the second and third order of consequences that employment involves. Also, from what we've learned is also that in discussions about AI technology or data science, it's not very useful to have them outside the context of the systems in which they're employed. So much of what we've examined was not just how the technology performs, but how it interacts with both the other legacy systems as well as the humans who operate them. Now, we're probably going to get a little technical. We're trying to avoid that as much as possible. So what we really want everyone to take away from this presentation is a feeling for the kinds of things soldiers of the very near future are going to have to know to fight effectively and ethically. To do that, we're going to try to introduce you to the kinds of things commanders, operators, staff are going to have to think about, and the kinds of conversations they're going to have in order to deploy this technology effectively. So with that as our scene setter, we're going to talk a little bit about professions and expert knowledge. So put simply, we have a particular view of profession here. Sometimes we use the word professional as to say, I get paid to do something, or that I'm very good at doing something. Here we're using a specific definition, understanding of it, where being in a profession entails having specialized knowledge that produces some sort of service to society, some kind of social good, that allows the professionals to exercise autonomy over what we'll call a specific jurisdiction. For example, let's talk about the medical profession. It involves specialized knowledge regarding human health that medical professionals apply to sustain or improve the health of their client. Because they have autonomy over that particular jurisdiction, health, doctors, for example, are allowed to do things like prescribe drugs, conduct surgery, or do other things that a non-professional would generally not be allowed to be. Now, when we're talking about the Army's expert knowledge, we map it into 4 different components. That map comes from work done previously by Don Snyder, Gail Watkins, and Rich Lackmont of the Army War College, but was later integrated into doctrine. And particularly, you find it in Army Doctrinal Reference Publication 1, titled The Army Profession. So this is how the Army understands its expert knowledge. We're using that as a framework to understand how AI is going to impact it. Put simply, technical expertise deals with and it breaks down into technical, human development, ethical, and political. The technical deals with ensuring the profession is effective. The human development, subsequently, involves recruiting the right kind of people to have that expert knowledge and employ it, as well as providing them with the right kind of professional development necessary to become effective leaders on their own. Ethical expertise determines the norms that govern the service the profession provides and ensures they are aligned with clients' values, international law, and any other relevant norms. Finally, with political expertise, in this case, covers how the Army in this case interacts with external actors, which includes other elements of DoD as well as the US government, as well as the American people and the government that represents them. Now, central to this, now in developing this expert knowledge for AI, to the extent that that expertise to develop algorithms, curate data, and do the other things we'll talk about here in a few minutes that are important to the application of artificial intelligence, to the extent that's going to lie in industry and academia, the private sector, as I just mentioned, there may be some critical expertise that lies outside the profession. To the extent that outcomes depend on machine thinking that is inaccessible to humans, some expertise may also lie outside the human. Now, to the extent the professionals do not have access to critical expertise, they risk ceding some autonomy and consequently jurisdiction. That cession impacts the kind of trust clients can have with the profession itself. Now, let's talk a few minutes about why trust is important here and why this is one of the central ideas we're organizing this project around. Because it's central to the professional status of the American military. At strategic levels, it shapes civil-military relations, where trust of the American people and the government that represents them not only impacts the role the military plays, the resources it is given, it also impacts, perhaps most importantly, who joins. At the operational and tactical levels, it stands as an essential pillar of command and control doctrine at both the joint and service levels. Military doctrine also underscores the bidirectional nature of this trust. It's not just one way, and it's not just about the technology. It's about mutual trust, which is shared confidence between commanders, subordinates, partners, and the equipment they operate, that they can be relied on and are competent in performing their assigned tasks. Trust enables things like mission command, allowing leaders to delegate appropriate decision-making and execution to subordinates, and freeing the commander to focus on those decisions that only they can make. The point here, and by describing it in these layered terms, is the optimized trust at any level. You have to optimize it at every level. So what I'm going to talk about now briefly is how AI impacts that knowledge and consequently trust. All right, so first we'll talk about the technical. In the targeting process under consideration here, in a few minutes we'll dive a little deeper into what that consists in. But briefly, AI facilitates sorting through data from sensors to identify targets, as well as potentially at least the assets that will engage the target. This process is an integrated process that requires prioritization of not just the target, but the resources dedicated to addressing them and the effects one desires to achieve. We can measure success and reliability in this regard in terms of the instances that the process identified a target correctly, failed to identify a target correctly, or identified something as a target incorrectly. Now, given the technical component, it's clear that soldiers are going to have to develop varying degrees of AI and data literacy. While identifying those varying degrees falls under the technical component, determining how to recruit, educate, train, and manage personnel with that knowledge will become a critical professional task. We can measure success here in terms of how well the system not only sustains the capability once developed, but responds to changes in the technology so that it evolves in order to maintain that critical advantage the technology is supposed to give. Now, regarding the ethical, this is basically preventing or mitigating. It starts with preventing or mitigating potential harm to non-combatants, as well as friendly forces. Given the potential for both friendly and non-combatant casualties, especially in large-scale combat operations that we'll talk about here, professionals will have to ensure the application represents an acceptable risk to protected persons. So we have to figure out how do we codify that kind of risk in a way that humans and machines can both understand it and meet the standard. It also raises questions of accountability. I'll talk a little bit more about this later, but briefly, as more of the decision process is given to the system, the process, we can end up having bad outcomes, even though all the humans have done everything right, and the machine worked as intended. That introduces what we'll call an accountability gap. We'll have to figure out how to address that in order to sustain effectively the application of this technology. Finally, the political. Given the ubiquity of AI applications and the way we think it's going to transform how we are going to think about warfighting and the roles that the humans are going to play in the process, it's going to have implications not only for civil-military relations, it's also going to affect how the various government stakeholders in a way that can affect the development of the application. Understanding understanding that impact and mitigating those negative effects will also be a critical task for professionals. Now we're going to talk a little bit about how artificial intelligence interacts with the targeting process. And I'm going to turn over to Colonel Elliott Harris, who's going to walk us through that. There you go.
And through the integration of these three main components, the targeting process seeks to synchronize both lethal and non-lethal actions to create desired effects and encompasses multiple disciplines and inputs from various staff elements and components within Army formations. Throughout the fire's warfighting function, targeting serves as the integral component of overall effort to generate effects that enable formations to achieve decisive victory in large-scale combat. The four-step targeting process focuses on decide, detect, deliver, and assess phases where artificial intelligence has the potential and capability to provide speed up through human-machine teaming. Commander's guidance and the development of targeting objectives occur within the decide phase of the targeting process, where the staff provides recommendations to the commander that include high-value target lists, attack guidance matrix, and other essential products that inform actions throughout the remainder of the targeting process. These products will allow both the employment of assets and capabilities to achieve the commander's targeting guidance. In the detect phase of the targeting process, this is the effort to synchronize observation platforms to identify and track approved targets from the decide phase across the battlefield. While this phase focuses on the management of manned and unmanned platforms and multiple other intelligence collection forms, it is designed to find, fix, and eventually conduct assessments of lethal and non-lethal actions across the battlefield. Simply put, from identification of a target to delivery, you potentially have seconds to minutes to be able to achieve an effect. So therefore, AI is essential to be able to accomplish that. Transitioning to the third phase or deliver phase, this is perhaps the most time-consuming effort within the process of where the targeting team determines the best shooter to engage the target to achieve those desired targeting objectives. During this step, the target is identified by an observer, and the mission routing packet is developed, which allows for the fire mission to flow to a respective shooter through a series of field artillery tactical data systems. This process is time-consuming based off the number of intervention points throughout the process from sensor to shooter that has the potential to generate recalculations and other delays within the process. At every echelon of the fire mission routing and the targeting process, there is the potential for delays due to dual independent checks that create redundancy in nature and can be mitigated through the implementation of artificial intelligence that Lieutenant Colonel Lowrance will talk about later. Finally, as we get into the last phase, the feed that feeds the remainder of the process, assessments are developed to determine if the targeting objectives were achieved. And within the complex environment of large-scale combat operations, the battlefield evolves rapidly. Artificial intelligence can rapidly scan the environment to make determinations of did we achieve the targeting objectives or have we created unintended or unanticipated consequences through our efforts. The targeting team completes target analysis, identifying the means that can be leveraged to generate desired effects, leveraging all available assets at their disposal. The efforts of the targeting team generate desired effects with the least risk and expenditure of time and resources possible. In accomplishing this, the entire staff is focused on achieving the commander's objectives. Through this process, the staff leverages the targeting methodology that is a rational and iterative process to methodically analyze, prioritize, and assign assets against targets systematically. Whereas the intent is intended to generate effects on the battlefield, speed is of the essence, and the integration of artificial intelligence into the targeting process has the potential to provide the capability for speed up that will ensure successful targeting and generate effects on the battlefield. It's important to note that while the targeting process is intended to be an automated process throughout the targeting cycle, it can become more efficient through the application of artificial intelligence. Most notably, targeting involves both deliberate and dynamic targeting that requires sensor-to-shooter pairing in order to generate effect. With respect to our deliberate targeting efforts, the sensor-to-shooter pairings are typically identified prior to identification and engagement of targets, which reduces the time from identification of a target to engagement of the target. However, within the dynamic targeting efforts, unintended targets require decisions that determine the best shooter to engage the target and thereby requires additional time for action for staff to formulate recommendations from sensor to shooter. Throughout both the deliberate and dynamic targeting process and the efforts within that, there are multiple entry points of information and friction where the process will consume precious time that could limit the ability to achieve an effect. As we look at how artificial intelligence can augment the decide, detect, deliver, and assess portions of the targeting process, I will talk about the conceptual aspects, and Lieutenant Colonel Lowrance will then provide some technical recommendations here briefly that will highlight that integration and how this is all possible. While the integration of artificial intelligence into the targeting process is already occurring in limited scope, as Dr. Pfaff mentioned, these efforts are not currently integrated into a collective process or a singular exercise that encompasses the entire decide, detect, deliver, and assess process. From a top-down focus, Army Futures Command Project Convergence has demonstrated the capability and capacity to integrate any sensor to the best shooter pairing through the leveraging of artificial intelligence with success. And subsequently, Project Ridgeway has demonstrated the bottom-up application of the fusion of intelligence information to be able to take multiple feeds from various intelligence sources that include imagery, signals, measurements, and multiple other intelligence collection platforms and fuse that together to identify targets. Without these artificial intelligence capabilities and speed up and the augmentation, it requires multiple intelligence professionals to fuse the data, make recommendations, and provide that information to the targeting team for action. Through this effort and the integration of artificial intelligence into the targeting team, the team can better manage mission accomplishment and achieve targeting objectives while accounting for collateral damage and risk to mission. At this time, I'll turn it over to Lieutenant Colonel Lowrance to talk the technical aspects.
I'm going to change it up over on this side of this podium here. If I can just turn on the mic. Here we go. All right, good afternoon, everyone. So, as Colonel Harris just mentioned, I'm going to be talking a little bit now about some technical details, but I'm going to keep it high level as much as possible. But first, we're going to talk about, one of the challenges to integrating AI is sometimes it can make mistakes, but so do humans, right? And so what kinds of mistakes does AI make? And what are those challenges? Because when mistakes are made by the system, that's obviously going to pull a little bit on the trust, right? How much can we trust the system if it's going to make mistakes? And so what are the types of mistakes we're talking about and what causes some of these? Well, AI, it requires data. And we call this first one the data challenge. Data, the AI algorithms, right, for an image classifier for targeting, for instance, might take geospatial intelligence information like a satellite image of the ground space, and then process that through a neural network, which will detect within that image particular targets. Well, to teach the system how to make such detections, you have to feed it data. Just like you would be teaching a child with cards saying, hey, this is an apple, this is a pickup truck. And iteratively, as you're feeding the AI algorithm numerous examples, it starts to pick up certain features, right? Hey, this looks like tracks of a tank. This is a turret. Sure enough, combine those two, I have a tank more than likely that I'm looking at here. And so, but to train these algorithms, they need an extensive amount of data. And that's part of the problem, is because how much data do we do? And it's kind of labor intensive, it's time consuming, because you have to annotate those data as you're going to see in a later slide. And think about all the possibilities of the numerous targets the Army might face. And AI is somewhat sensitive now to various conditions, like lighting conditions or weather, the backdrop of the environment. And if you start to make all these combinations and put them together, you're talking about an exponential volume of data that's required. And so that's part of the challenge. And then next, well, because maybe you have a new input to your system that's not representative of the data that you trained your algorithm, you might have some errors as a result. And what kind of errors are we talking about? Kind of on the mild side, you might have a misclassification where the AI algorithm says that, hey, this looks like a T-90. Well, in fact, it's a T-72 tank. Well, that's maybe an example of a kind of a mild mistake. On the more, as the slide says, maybe it's a school bus that it sees and it looks like a missile launcher. Well, that's a misclassification of what actually is represented in the image. False positives is an example of where the AI algorithm is telling you that a target persists in the environment, or in this case, the example that I used earlier of an image, maybe a satellite image or a ground-based image, and says there's a target there, but in fact there's not. Next, false negatives. These are when the algorithm would fail to detect the target, even though it is actually present in the data sample. And again, we're kind of working off the use case that we're talking about imagery. All right, other types of vulnerabilities is basically, the enemy could potentially try to fool our system. And how could they do that? They could do so by camouflaging their equipment, for example. Maybe we don't have enough imagery or examples that we taught the algorithm of tanks in defilade positions or with camouflage netting over them. Or they changed the color of their tanks. If we're looking at a colored image, maybe they changed it from green to kind of a grayish color. And then they can also try to maybe worst case, get a hold of our data. If we weren't able to protect our training set of data, they got a hold of that. They can maybe put some malicious images in there that makes our system more vulnerable, more susceptible to not detecting them, for instance. Well, fortunately, we can mitigate those concerns I just laid out in the previous slide, but how do we do that? And you kind of have a laundry list, and I'm going to kind of walk through each one of these to talk a little bit in detail about how we mitigate those concerns in the previous slide so that we can leverage AI in the targeting process. First, as Colonel Harris was mentioning earlier, is that we can use sensor fusion. As you saw on his slide, he listed lots of different types of intelligence feeds that we can use as part of the targeting process. Well, combining those together, providing those to the AI algorithm, it can leverage that information because each sensor feed provides new information that it can use to mitigate, for instance, maybe the image, the geospatial image, failed to detect the target. However, you have electronic or signal intelligence feed combined maybe with some human intelligence suspecting that targets are in the area, and together that mitigates the failed detection on the image side to still give you some level of confidence that a target persists in that area. Also, we can mitigate it through retraining our algorithms, meaning I gave you the example about the flashcards, right, of teaching the algorithm to detect targets. Well, if you notice a system fails to detect a particular target while it's deployed, you can take that information, that data example, add it to your training set, your set of pool of examples to the algorithm, and that gives it additional information to learn from. So just like a child would potentially make a mistake as you're trying to teach them how to read or recognize objects and know the names of those objects, well, you just reinforce it. You provide them feedback. The same kind of information we can do, the same type of approach we can apply for the AI algorithm. And that is going to be very, very critical because we know, as I talked about the data challenge, it takes a lot of data to teach these algorithms. Well, that you're going to have to collect over time. As the system's operational, keep training the system, keep improving it over time. Next, we're going to have robust test and evaluation processes. And part of that, one of the classical approaches is that you're going to have a training set, a pool of images, for instance, to teach your algorithm. Well, you don't provide the same set of images for your testing because you want to have a holdout set where you keep that information away from the AI algorithm and then test it against that information or images, for instance, that it's never seen before. And then you can start to build some statistics on how well the algorithm is performing. And then as you start to use it, it's deployed, you're evaluating, you're monitoring, you're supervising the system, you can still continue to generate statistics on performance. Commander's risk acceptance. Dr. Pfaff mentioned a lot about risk and trust already. This is a critical element. If you look at different types of operations that commanders face, they're going to face different scenarios where they are going to have changes in mission that's going to change the way that they look at how much risk they're willing to tolerate. For example, if you have a counterinsurgency operation compared to a large-scale ground combat operations. Well, counterinsurgency, right? Generally speaking, you have insurgents that are trying to hide within the populace, masking themselves. You're trying to not agitate the populace, right? You're trying to do security operations. You have to be very careful in those types of targeting processes. So you're going to be less willing as a commander to take risk in those types of operations. Where if you're fighting a near-peer threat in large-scale combat operations, and you are expecting an enemy to be out in the open, maybe you're not fighting yet in an urban environment, well, you as the commander are probably willing to take a little bit more risk with your operations and your targeting process. And that's going to come into how we're going to incorporate AI smartly and wisely into this process. Training and teaming, of course, we're not trying to replace humans completely in this process, right? We know that humans are going to have to supervise appropriately this type of, human-machine teaming, and it needs to be adaptive. It can't be just necessarily static all the time, where you say the human needs to double check every time the AI generates an output. That might still we still have a bottleneck problem in that case, right? Where we're not necessarily we're limited on how much speed up and how much acceleration we can get in the process. But can we do so smartly, wisely, responsibly, in line with our ethics? And we're going to talk about that as well. And really, to do that approach and to do so quickly and smartly, we need an intelligent control system. We need a system that is able to assess the situation, assess what the AI is telling us, and assess what the commander's intent and risk acceptance is, and then combine those together and make a wise decision. And so the next couple slides, I'm going to talk a little bit about how do we do this in an kind of a controller design aspect. This is where it gets a little bit technical, but I'll keep this high level from the perspective of a commander and what they need to know to understand the system so that it can be deployed the most effectively. So a couple of inputs into this system that we're going to leverage to do this responsibly. One is the confidence of the AI algorithm. And if you go back to my previous slide here, you can see of an example of a training example to teach the AI algorithm to recognize targets. Here you have a BTR-80, like an armored personnel carrier. You have a tank here, a T-72 type. Well, this takes human annotation, right? Humans to click and drag over the target, annotate it, and get enough of these examples to feed through the neural network so that it learns the features and learns how to classify these targets. And then it provides a confidence score, actually, a probability, a measure of confidence that it has that what you see here is a BTR-80. But how sure is the algorithm? Well, the algorithm will tell you. It will say, I'm 80% sure this is a BTR-80, for example. And if it's less confident, it might go up an ontology scheme or a hierarchy and say, well, I'm not sure it's a BTR-80, but I know it's a wheeled vehicle, right? A military wheeled vehicle or a tracked military vehicle. And so therefore, in that case, that's when the AI algorithm should cue a human analyst to say, well, let's just tell me it's a military vehicle. Am I looking at a friendly or an enemy vehicle? And so we're going to take that input from the AI system, and that gives a scale, a probability scale that ranges from 0 to 1 or 0 to 100%. And then we're also going to have a rheostat knob for the commander, that the commander can adjust and tune based on those operational conditions that I described previously. And can we wisely combine those two to make an automated recommendation on how we should process the targets in more of a risk profile manner, right? And again, this goes to this adaptive teaming aspect. Do I need to check everything the AI algorithm does, or should I have a little bit more trust in the system to execute some functions? And then I'll kind of do a final check at the end, for example. And this is where we propose a fuzzy controller. And so this is a well-known engineering design approach. And fuzzy logic, I'm just going to keep it kind of high level here. It's really neat because it allows you to leverage expert knowledge into the system and build human-based linguistic rules for the decisions that should be made. So you're basically imparting expert knowledge and wisdom into the system through rules that are human legible, like this. You can say, and this is just one example of, let's say, a 9 base, and you're going to see in the next slide, a rule base that consists of 9 rules. So if the commander's risk tolerance is high and the AI confidence is high, what is that telling us? Logically, that's saying the algorithm's pretty sure there's a target there. The commander's saying, hey, I'm willing to accept a lot of risk. Maybe he's facing a large-scale, near-peer threat, large-scale combat operations. Then therefore, my supervision can be a little less, right? We're not saying no supervision, but appropriate level of supervision. And that is kind of the gist of fuzzy logic, and it allows you to build this type of system. There is some classical set theory and some technical details about fuzzy logic. Know this, that fuzzy, where it gets its name, it's a little bit of a misnomer, but it allows you to deal with sensor measurements with some uncertainty that are in them. Classical set theory says, well, if I wanted to split off some thresholds and say, well, Commander, let me take Commander's risk tolerance, and I want to break it off into low, moderate, and high, so I can build some rules. Well, 33%, 66% are my cutoffs, right? And you either belong or you don't to one of those based on where that rheostat knob is for the commander. Well, fuzzy set logic allows you to partially belong. There's some fuzzy regions here where there's some overlap. And this is, again, designed by a human expert, where you can have some overlap and say, well, maybe here I am 20% in the moderate, 80% in the low, right? And so you can kind of partially belong. And what that does is it allows you to have a rule base here. Maybe multiple rules get fired, meaning they get partially on based on their degree of membership that they belong. And so this is a block diagram of the entire system. And this is, again, from the commander's perspective of what they really need to understand. They, one, need to understand the inputs into the system and know that it's extensible as well, that you can add additional inputs. But using our case example, we've talked about these two inputs. Well, here's the rule base I talked about with fuzzy logic, where you can have a set of rules, and you can kind of work through the matrix here and see, you know, for instance, if my risk tolerance is low and my AI confidence is low, then I'm in this box here, and that's telling me, logically, right, there'd be a rule. What should I do? I should have maximum oversight, right? Because my AI algorithm is saying it's not so sure about what it's looking at. The commander is saying, hey, I don't want to take too many risks here. I'm maybe facing a counterinsurgency type of operation. And so I need maximum oversight of the AI at this point in time. And I put this in here. This is, again, another version of the targeting cycle known as find, fix, target, engage, and assess. And I put some sub-processes, and Colonel Harris talked about some of these, about pairing the targets with the right effect solution, and also air and ground integration. Well, we can actually use AI for those processes as well. This is really an optimization function, and AI does a great job at optimization problems, where what is the best effect for this type of target scenario? And then if you look at air-ground integration, well, that's the whole point of I want to minimize any unintended consequences, like fratricide or collateral damage. Well, the Army, is one of these modernization programs, is building what's called One World Terrain, where the goal of that program is to build a 3D terrain map of the world. And AI can look at that based on, for instance, we have a target that's been detected. We know the geolocation of that target. We can go into One World Terrain. Is there any objects around? Is there schools, religious sites, and so on, that maybe would cause some issues, obviously, with unintended consequences? Well, we can start to assess what is the potential chances or risk. And we can add it into an expert knowledge type of system like this and build new rules for automating. Because what we want to do is we want the system to wisely tell us very quickly, what level of oversight do I want? Do I want maximum, moderate, minimum, for example? And your next question is probably, what does that look like when I'm talking about levels of supervision? And as I said earlier, we're not talking about removing the humans out of the loop. We want humans still in the loop. And that's what this last step is, this validate and authorization step. We still want the targeting officer or fire support coordination officer in the loop that's making this the final call to say, yes, this is a valid target. This meets the law of war, of armed conflict, my rules of engagement. It is a valid target to engage, right? That's still going to be reserved, as you can see, by the color code for a human decision. Now, what you see here is levels of oversight. And these are the categories we discussed earlier, and you have a risk profile or a flow for each one of those. So let's talk about the maximum. The maximum is, you can see the soldier in each one of these, or the warfighter. that represents that each one of these steps still needs to be checked, human validated. Doesn't mean that AI might not be augmenting or assisting. AI might be still finding and fixing and tracking targets and providing that information, but it needs to be verified by a human. The solution pairing, right? Double check, make sure that munition is correct that we want to fire or that effect, and then do the double check on the air-ground solution integration. And then on the opposite end of the spectrum, what's the minimum look like? Well, this is where we get the acceleration based on those other criteria we talked about. And this is the whole concept of adaptive teaming, adaptive human-machine teaming. Well, this would be led by AI. Same here with degree, these would be AI functions, but again, the final step would be reserved for that final validation, authorization by the human in the loop. Okay, so with that, I'm going to turn it back over to Dr. Pfaff.
Well, thanks for that, Chris. So what I'm going to do for the rest of the presentation is kind of briefly go through the other elements of expert knowledge and discuss how all the things we've talked about here are going to impact our ability to, again, maintain the status of the profession, provide that service that the American people, expect us to provide. So the first thing we're going to talk about is human development and how do we manage talent. And as we noted before, the challenges that this technology, as Chris aptly demonstrated, can be very specialized. While at the same time, we need a lot of people who understand those sorts of things. We're not quite yet up to managing that. So here's sort of the problem in a nutshell. Right now, if you're an officer or someone with a STEM skill of any kind, you can only be assigned outside your branch if the branch has filled all of its slots and where they want you in that skill or capability, there's a generalist position available. So for example, if we had a functional area 52, which is nuclear and countering WMD officers, but who had AI experience, we could only put that person where that experience could be utilized if there was that generalist position. Or you can do it if there's no position available, but that takes very high level, 3-star kind of engagement, which is not necessarily very, it can be not very flexible and difficult to manage. And so for the record, just so you know, at the core where we've been kind of operating, in terms of STEM skills, for the most part, they're authorized 4 space officers and 3 simulation knowledge management officers who might have some of the relevant skills that are necessary to manage this system. Obviously, we want to be able to figure out ways to provide more. Now, regarding STEM skills in the military in general, a lot of that comes through the advanced civil schooling process. And last fiscal year, of the 174 authorizations, 72 of them were for STEM degrees, which is less than 50%. Now, the Army, in response, has started in 2020 a 2-year master's degree called the AI Professional Scholars Program, which is done in conjunction with Carnegie Mellon University. The first 20 graduates are expected this year in the summer. Also, you have academies like West Point that also recruit and train and educate STEM skills in their faculty. But the difficulty here is that they can sometimes be hard to track. For example, my friend Chris, he has a PhD in computer science. That's what it says on his record. He also has a concentration within that PhD on artificial intelligence and robotics. That's not on his record. So if you want to go find Chris, make use of his AI capabilities, he has to either have voluntarily told and figured out how to do that. There's a process called knowledge, skills, and behavior. He has to actually told them that he has those skills, or he has to just be known for it. It's not a very systematic way to go about it. Similarly for West Pointer, I'm like a West Point professor who might be an engineer, but their degree is in, maybe have a degree in artificial intelligence, but then again gets labeled as something else. They're going to be kind of hard to find because engineering branch may not be tracking that person that way. And while you can search on majors and academic degrees, they're not really standardized. So as Chris's example illustrates, a lot can still get lost. So we need to kind of figure out ways to find out what we have so that we know what we have to develop. So our recommendations that we're looking at right now, we're still kind of trying to figure a lot of this out, But obviously, we're going to have to figure out what general sort of AI and data literacy education we need to do. One other thought that people have come up with that has been proposed by actually a number of folks is to create something like a technology core that's not just limited to one branch or functional area, but functions like the logistics core does now, where it's comprised of 3 other branches: ordnance, quartermaster, and transportation. So using something a bit more broader to manage that talent, as well as create additional skill identifiers so that you can somehow get certified as having that particular skill, and that allows us to track you so that we can put you where that's needed. You're also going to have to figure out how to fix the billeting situation, where you can like multi-code certain particularly general positions so that someone with a particular skill indicator can actually be assigned to that position in a more systematic fashion. So that's kind of that in a nutshell. I'll talk real briefly about ethics and governance. Now, okay, good. So first I'll step back a second and just I want to frame military ethical decision making in a kind of context that makes sense here. Because when you're out there and you're fighting and in combat, military ethical decision making is often about making different trade-offs, particularly different trade-offs between what it takes to win, military necessity, force protection, and avoiding collateral harms. Now, military operations obviously place soldiers and civilians at risk. Now, we can reduce that risk to soldiers by limiting their exposure to harm. However, depending on how we do that, we might increase risk to winning or to civilians and non-combatants. Now, we can prioritize avoiding harm to non-combatants. However, again, depending on how we do it, we can increase risk to accomplishing the necessary, to winning, accomplishing the necessary missions, or increasing risk to soldiers who may otherwise be required to increase their exposure to harm in order to avoid harm to non-combatants. Now, AI can impact that trade-off in a couple of ways. Because artificial AI-enabled systems are not subject to things, for example, as fatigue, cognitive impairment, or motivated by self-preservation, fear, anger, or any other negative emotion, often they're better at avoiding violations of things like the War Convention or the law of armed conflict, often than human counterparts. So, done right, the application of these technologies can actually lower the overall risk because in allowing greater speed, precision, and accuracy, it makes winning more likely, and which, if done better than the adversary, reduces risk to soldiers, and to the extent is more precise and accurate, limits overall destruction, reducing risk to non-combatants. But, as we've said a couple times today, both humans and machines can make mistakes, and how one handles those mistakes is going to impact how we're able to employ and sustain the technology. And that works out in 2 ways. One is what I talked about earlier, is the accountability gap. The other thing, that's the problem with the machine. There's also the problem with the humans, we'll call it automation bias, where a human, for any number of reasons, might uncritically accept the machine's judgment without properly conducting the oversight that Chris was talking about. So first, really quick on the accountability gap. One problem with AI, particularly with those that are involved, that utilize neural networks, but even when it's just code, it's not always clear why the machine did what it did. That makes machine thinking sometimes something of a black box. When it is a black box, sometimes humans may not understand why the machine produced a particular output that it did. Moreover, that output might entail violations of something like the laws of wars or other relevant norms that humans may not perceive in time to intervene. Even more to the point, and this is the big takeaway, is that can happen when humans have done everything right and the machine is working properly. That means there's the potential for norm violations for which no one is accountable. Now, why is that a problem? Well, put simply, norms, whatever form they come in, are the means by which we hold others and ourselves accountable. But when they're not upheld, they die. For example, consider a workplace environment where you have a norm to show up on time. Let's say some people don't show up on time. If they're not held accountable, it's very likely more people won't show up on time. Pretty soon, that norm to show up on time no longer is a norm. And the employment of AI systems could produce certain incentives that will undermine the application of things, again, like the law of armed conflict. The fact that certain AI applications can absolve humans of accountability for at least some violations will establish an incentive to employ them more often and find ways to blame them even when something goes wrong and even when a human is actually responsible. It's not hard to imagine that over time there could be sufficient unaccountable violations that the rules themselves are rarely applied even to humans. Now you might say, well, let's just make the humans accountable. And I'll call that absolute accountability. But that's not much of a better solution. Telling commanders, operators, and other stakeholders they may be liable for violations that they neither committed nor intended, which is the legal standard for responsibility, could disincentivize the use of the technology, which then places missions and soldiers at risk. So we have to figure out how to address that concern. On the flip side, we need to talk about automation bias. Now, probably many of you are familiar with the Vincennes incident, where an American Aegis-class destroyer shot down an Iranian airliner back in the 80s. Now, this was a very simple automated system. Nothing that we're talking about, nothing like what we're talking about here, but still, the machine incorrectly interpreted data that had the humans looked at the data, they would have said, this can't be right, and the machine interpreted the data as an incoming Iranian aircraft to attack the ship. The humans, even though the humans still gave the order to fire, they gave the order to fire because they believed the machine and didn't really review that information. They trusted the machine. That was of the very simple system. Probably going to get a lot worse. So that kind of dependency could get worse over time, particularly with the kinds of advances and particularly with the kind of reliability we expect from these machines. So what do we do? Well, the way ahead then lies in reducing risk to a point where the AI-enabled systems, I think, performs at least as well, if not better, than the human-only process. To do that, to get there, that requires two things. That the logic that drives the controller that Chris was talking about needs to account for the demands of the law of armed conflict. Second, we've talked about how we're going to curate data so we can identify high-value targets. You can enhance your ability to conform to the law of armed conflict if you also code or curate data to identify things that you don't want to target, like churches and hospitals and things like that. So not only code for the right things, code for avoiding the wrong things as well. And then finally, for automation bias, it's important to ensure operators and commanders can explain and know they have to explain and have the burden to explain why a particular AI-enabled process produces the output that it did. And getting to that point will require what we were talking about before. That will have to be integrated into the more broader AI literacy education and training that we were discussing. All right. Finally, we'll talk a little bit about the political. AI impacts the political in two ways. The first is through the civil-military relationship. For those of you who read Peter Singer's book, about 10 years old now, Wired for War, he made the point that even back then, employing highly specialized technologies can be better served by contractors or civilians. And we're seeing that here. There's often a lot of reliance on contractors and vendors for operating algorithms, developing them, and so on. A lot of this expertise relies outside the Army. Now, such reliance could affect the professional status because if that expert knowledge required to provide the service, defense, for the nation becomes predominantly employed by civilians, it is arguable that the military will not retain its professional status and rather be better characterized as a technocratic bureaucracy that manages civilian and other skills and capabilities while a relatively few members bear the burden of risk. Now, we can overstate that, and we don't want to overstate that, but it's important to understand that things can drift that way if we don't pay attention to it. Because this reduction of risk, which is arguably the point of military innovation in general, that could have the most disruptive impact on the military-civilian relationship. Society rewards soldiers precisely because they expose themselves to risks and hardships on their behalf. However, to the extent soldiers neither experience risk nor sacrifice, they may be likely better thought of as technicians and warriors. And while enhancing soldier survivability and lethality always makes sense, enhancing it to the point of near invulnerability or limiting the numbers of folks who are actually exposed to risk and hardship, it's going to profoundly affect what it means to be in the military and how society treats it. And that's not necessarily a bad thing, but it needs to be it needs to be managed and accounted for. And finally, our conclusion. All right, I think I'm right on time. What I hope you got out of this, now what we didn't do, obviously, is we didn't make the decisions we teed up in the beginning. Probably didn't answer all the questions, because right now we don't necessarily have them. But what I hope we got out of this was how we were going to go about solving the problems that we raised and evolving this technology into the future to not only maintain advantage over our adversaries, but sure that we do that in a responsible and ethical way. And on that cheerful note, thank you very much for your attention.